Alright, hi everyone. So for those of you who don't know me, I'm Miss Hu, your physics teacher. Now in this video, we will be discussing the solutions to the questions in topic 1.3, forces and equilibrium as provided in this book, the module book, Form 5, Tugasan 3, page 25 onwards. So the reason I'm also preparing this video is because I believe it will be beneficial for students who have this book. And just to let you know, I have the teacher's edition here, and many of the answers in this teacher's edition is unfortunately incorrect. So I've also created this video in order to help students work towards the correct answer. I'm just going to move my face out of the way. Okay. And in case you're wondering why my eyes are going in this direction, it's because my second screen is up on this side, and when I work on my tablet, it's working with the Jamboard that's on this screen here. All right, so let's get started. By the way, this video is not meant to give you free questions. If you don't have the questions, then you need to go and buy the book. I earn no commission or royalties from this book. I did not prepare this book. I do not earn anything from any sales of this book. But I'm preparing this video anyway because this is the book that my students are using in class. And that's why I'm preparing this video for their benefit mainly, but hopefully for the rest of you out there as well. Now, of course, I have included diagrams from the questions in order to help with the explanation. So let's take a look. Now, for this particular exercise, Tugasan 3, there are 3 diagrams provided, and for each of these diagrams, we need to come up with the answers to 4 different questions. You need to draw the triangle of forces. You need to calculate the unknown forces. You need to draw the triangle of forces to scale, and we need to work out the vector force table. So I'll explain the answers for all, and you check your answers whether you got this correct. Okay, so let's start with this first diagram. Now, in this question, they've given us a situation where there's a girl hanging from something, which they didn't explain. It's just she's hanging there. We're going to assume that she's on something similar to Firefox, except she's sitting down. And there are 2 forces, a string with 2 different tensions on both sides supporting her. And we'll assume that this is an equilibrium because this is a topic of equilibrium, right? Okay, so they've also given us the free body diagram. Now, just a reminder that 60 kilogram in your syllabus of KSSM, it's not 600 Newton. By right, if you use your calculator, which I'm pulling up off screen right now, 60 kilogram times 9.81 should give you 588.6 Newton weight. And that's the value that we should be using. However, because this question already wrote 600 Newton, we'll stick to 600 Newton for the purposes of this for this question. So let's draw the triangle of forces. We already have the free body diagram. So how do we come up with the triangle of forces? We have I'm going to start with the weight line because that's the vertical line, so that's the easiest reference point. So we're going to draw a weight line. Now remember that the triangle of forces do not have to be to scale. It just has to be a sketch complete with all the forces labeled and the angles. The line's a little bit thin, so I'm going to switch my pen to the thicker one so that it's more visible in this video. Okay, and here's the weight of 600 Newton. So we've got T1 going up. You can either draw T1 or T2, but because I've drawn it this way, there's no space for T1. So I'm going to draw T2 from the tip of this arrow up diagonally to the right. Label this as T2. And then complete the triangle with a line that goes up diagonally left, T1. Now, remember, we don't have to draw it to scale, but you must have the labels of the forces, which in this case are W, T2, and T1, as well as the angles. So the angle of 30 is between T2 and the horizontal. So T2 and the horizontal, which I will mark here with a dotted line. This angle is 30 degrees, which means that if you want to label the angle on the inside, it's actually 60. T1 angle from the horizontal is 45, which means that this is 45. Let me make it dotted. So remember that it has to be a dotted line if it's not actually part of the triangle. That means it's not an actual force line, it's merely a guideline. That's why I always draw dotted. So 45. So if we have a triangle this way, that means this is also 45. Because of the Z rule, this would be 30 degrees. And there you go. This is your triangle force for this particular question. Now, to resolve the forces, actually it's to solve the forces. In the question it wrote there resolving forces, but what we actually want to do is we want to find the value of T1 and T2. So now to find the value of T1 and T2, there are two methods. You can use the resolution of forces method, or you can use the triangle of forces method. If you're not familiar with both methods, I suggest that you watch my video first, which the link is provided there, on how to use these two methods to solve forces and equilibrium problems. So if we were to resolve these forces, actually we should take the free body diagram. So let me take this, and here I'm just going to remove this, and we're going to focus on this diagram. Okay, so when you resolve the forces, you need to resolve the forces that are acting at an angle. So that means we need to resolve T1 and T2. So I'm going to draw with different colors here for clarity. We have green on this side, we have T1's horizontal and T2's vertical. So I'm going to label that as T1x and T1y. For T2, we also need to find the horizontal and the vertical. So we will have T2x and T2y. So in this case, it's a little bit challenging because the values of T1 and T2 are not equal. So you cannot assume that all of these are equal. Whoops, just give me a moment. Okay, but we can use logic in this case to work out which one is equal to which one. So you can see over here, in terms of the horizontal components, there are only two. And if they're in equilibrium, that means these two must be equal to each other. So although the values of T1 and T2 are not the same and the angles are not the same, however, due to the presence of only two forces, we therefore can conclude T1x is equal to T2x. So I'm going to write that down. Let's use the color just because. So T1x equals to T2x. And then for the vertical components, you can see that there are two vertical forces upwards and one vertical force downwards, which means that the sum of these two will be equal to this. So I'm going to write that down as well. T1y plus T2y equals to 600. So we need to then, of course, before we continue, then we need to resolve the values of T1x and T1y as well as T2x and T2y. So you can see from this triangle, the angle is here because T1x is adjacent, and I'll just use a shortcut right now. Okay, no, let's work it out for the benefit of those who need to see it. T1x over T1 is adjacent over hypotenuse. That gives us cos 45, which means that T1x is T1 cos 45. So in the same vein, for T1y opposite over hypotenuse of T1, that gives us sine. So that means T1y equals to T1 sine 45. Now what we have here is still a bunch of unknown values, but it's all right. We'll reduce it down to the expression of T1 so that we can solve it, and you'll see in a moment why. So the same thing will happen for the T2 triangle. So you have T2x over T2, which is adjacent over hypotenuse. That gives us cos. So T2x equals T2 cos 30. And the same thing will now be applied to T2y. T2y is opposite, and T2 is a hypotenuse. Opposite over hypotenuse gives us sine 30. So that gives us T2y equals T2 sine 30. Now, with so many unknowns, how do we solve this question? So this is going to require us to use simultaneous equations. So now we have these two. What we're going to do is we're going to take all these T2 cos T for whatever and put them into these two equations. So from the first equation, let me do it like this. T1x is T1 cos 45 and T2x is T2 cos 30. So from here, if we work it out, I'm using my calculator off screen, you'll get 0.707 T1 and T2 cos 30. Cos 30 is 0.866, so it's 0.866 T2. So why do we have this? Because then what we can do is we can find, let's say T1 expressed in T2 or T2 expressed as T1. So for this, let's express it as T1. So that's 0.866 divided by 0.707. Whoops, data did not register that. Let's try that again. 0.866 divided by 0.707. That gives us 1.225 T2. So this is from our first equation. We have come up with this. I'll just write it as 1 and 2 for clarity. So from 1, we now have 3. Yeah, you know what? Let's write that. Let's remove the arrow. From 1. Okay, so what we're going to do now is we're going to solve 2, but there's not much space. So I'm just going to create another blank slide so that it's easier, right? So from 2, I'll just rewrite the equation. So T1y plus T2y equals to 600. Now we know that T1y is T1 sine 45. So it's T1 sine 45. T2y is T2 sine 30. So T2 sine 30, that gives us 600. So let's find the sine values first. So sine 45 is 0.707 T1 and sine 30 is half. Okay, so then how do we solve it next? We know from number 3, T1 is 1.225 T2. So from 3, we're going to sub that in. 1.2, whoops, 0.707 times 1.225, whoops, T2 plus 0.5 T2, that gives us 600. So solving that using my off-screen calculator, we get 0.86, whoops, I said 608, 0.866 T2 plus 0.5 T2, which gives us a total of 600. So adding that together, we have 1.366 T2 equals 600. So 600, it's not registering, 600 divided by 1.366 gives us a value of T2 of 439.24 Newton. And then to solve T1, because we know T1 is 1.225 T2, right? So 1.225 times 439.24. I am typing that into my calculator. Oops. That gives us 538.07 Newton. And that's how we can solve this question using the resolution of forces method. By the way, if you had watched my earlier video where I divided the triangle into 2, this that wouldn't work. Oh, that doesn't apply for this. Let me talk about that in the next section. Sorry, I got ahead of myself. Okay, so that's with the resolution of forces. Now, if you want to solve this using the triangle of forces, you need to draw the complete triangle first. So using the free body diagram, in fact, let's get the free body diagram again, which is this. I'm going to remove this. Okay. So the free body diagram, I'm just going to make this a bit smaller so that we have more space for our triangle of forces. Okay, we have the 600. Oh no, in fact, you know what? Let's just take it from here because we already have this diagram, right? Okay, so from here, right, you can also, okay, so earlier I was talking about dividing the triangle to two. So if you watch my earlier video on the textbook example, where I said you can divide the triangle into two, you can't do it in this case because T1 and T2 are not equal. So if you try dividing this triangle into two, and you say, oh, this is W over 2, 300, and W over 2, 300, that's not the case because if we divide it, you can see that it's not an equal split. So you can't divide it using that method. So instead, how to solve this is you'll have to either use the sine rule or you can divide this into two and find again T1 cos 45, T1 sine 45, T2 cos 30, and T2 sine 30, which means you have to use the resolution of forces method again, which is pretty much what we have already solved over here. So I'm not going to use that method. Sorry, I'm not going to use that method. Instead, we'll focus on the sine rule, which was also explained in my earlier video. So the sine rule, remember that basically, even if you haven't learned at maths or you don't take that, not haven't learned, even if you don't take at maths, you can still use this method. It's not difficult. Basically, it's the length of one side, or in this case, the force, over the sine of the opposite angle. So for example, T1 opposite would be 60. Okay. So this is the rule for all three sides. So if we were to substitute it, and if you like to know how to use it, it's not difficult. So let's say T1, opposite angle, not where T1 is, right? Opposite is 60, the internal angle, so that's sine 60. T2, opposite is 45. And W, the sum of these two are 75, right? So sine 75. So how you solve it is, because this equal, you can either take this equal to this or this equals to this. Now we know that W is 600, so I'm going to replace the value here with 600 and let's solve it. So which means that you can write it as T1 over sine 60 equals to 600 over sine 75, and we can solve it from here. 600 over sine 75 times sine 60, which gives us, so I'm going to just use my off-screen calculator. Sine times 60, and you will get 537.95 Newton. Then we're going to do the same thing for T2. Let me create a blank slide here. Okay, and I'm just going to take these numbers and put it here. Solving it. T2 equals to 600 over sine 75 times sine 45. Then that gives us 439.23 Newton. And there you go. So you might find the numbers that we obtained in this second method are slightly different from the first, but they're almost the same. So there will be margins of error because we've rounded up the numbers due to the sine angles. So if you actually use your calculator, you'll find that the sine angles, the decimals go on forever, but we've rounded it up. So that's why there's a little bit of error on the numbers, but you'll find that the numbers are close enough. So as long as they're close to the actual value, they'll still be accepted. Let's go to B2, which is drawing triangles of forces to scale. Okay. Keep putting this diagram. I should put the other diagram right. Yeah. In fact, no, let's take the triangle. And I won't go through this in much detail, but basically, you just need to draw this to scale in your paper. So given that the question has already stated 1 cm is equivalent to 100 Newton, so use your ruler to measure out. This should be 6 centimeters. Use your protractor to get the angles. So what happens is you draw this, you draw this line first. If you don't know how to draw T1 and T2, measure this angle out and draw this line. And then from here, measure this angle out, draw this line. You'll find that they will both intersect. Then to get the values of T1 and T2, just use your ruler, measure this out, you can get the value. So the expected answer you should get. Now you're not going to get decimals obviously because it's drawing, and if you measure this out, you should get about T1 will be about 5.4 centimeters. So 5.4 times 100 gives you 540 Newton. T2, you'll get about 4.4 centimeters. So that will be, using the conversion, you will get 440 Newton. So it's close to the values as you can see, which means that, yeah, you got it right. Now, for the vector force table, what are you supposed to do? The vector force table is essentially it's a lab kit for you um, to do the experiment in lab to prove forces in equilibrium. And what they want you to do in this question is to just draw how you should be placing the string in order to study forces in equilibrium. So it's not difficult. This is what you do. Let me just give you the answer over here. Based on this, we can see that, okay, we'll take this line as like the horizontal. So T2 is 30 degrees from the horizontal. So from the horizontal, 30 degrees, you can draw out T2. T1 is 45 from the horizontal, so you measure out 45 using the protractor on the vector force table to help you get T1. And weight, of course, is vertically down, so vertically down. So this is what you draw in the vector force table function. Okay, let's now look at situation 2. So for situation 2, it's much more straightforward. And although it's not labeled in the diagram, it's actually 90 degrees over here. Okay, so the triangle of forces is much clearer because 90 degrees is so easy to draw, right? So an example of the correct answer would be this. We've got T3 going down to the left, T2, and up this way, T1. Now, 60 degrees is between T1 and the horizontal, which means that, actually, let me move T1 label a little bit down. That means this is 60 degrees. This line, of course, should be dotted because it's a guideline. It's not an actual force line. That means that this is 30 degrees on the inside. This is 90 degrees. Therefore, this would be 60 degrees. So to solve the question, I set this up without checking, but actually you can solve this straight away with the triangle of forces method. But I'll use both anyway for the sake of completion. Hold on. Let me change my pen. Okay. So some students may prefer resolution of forces. So let me remove this and use the free body diagram. So here, what we do is we resolve the force that's at an angle, which is T1. So T1, I'll do this here. So T1x and that's T1y. My bad. T1y and T1x. So T1x, you can see is adjacent. So T1x over T1 gives us adjacent over hypotenuse cos 60. And T1x will be T1 cos 60. T2y is opposite over T1 sine, opposite over hypotenuse is sine, giving us, we have a T2y, T1y. T1y equals T1 sine 60. So to solve this, remember that all the horizontal components will be equal to each other, right? So let's use blue. T1x equals to T2, which means T1 cos 60 equals T2. Now we've got two unknowns over here. So let's look at the other comparison, which is T1y. So T1y equals to T3, which is 100. So I'll just write 100 here straight away. T1y is T1 sine 60, which is 100. And from here you can solve T1. So this gives us 100 divided by sine 60, which is, let's do this off screen because I don't want to use the numbers in the book because it's always not correct, right? 100 over sine 60 gives us 115.47 Newton. So to solve T2, we take from number 1. That means 115.47 cos 60 is equals to T2, which means T2 is equal to 57.74 Newton. And that's your answer. If you prefer to use a triangle of forces method, let's get the triangle then, because it's easier, right? So I'm just going to put the diagram in there for easier reference. We can just get rid of this. We already know that T3 is 100 Newton, so I'm just going to add that in here. So to solve this, we can just use a triangle straight away, and I'm going to use 60 degrees as our base. So taking T1, I'm just going to change color. T1, sorry, not T1. T1 is the hypotenuse. So let's label that 60 degrees, right? This is adjacent, this is opposite. So taking T3 over T1, T3 is the opposite to the hypotenuse. So that means this is sine 60. I'm just going to put the value of T3 in here so that it's easier for us to calculate straight away. So T1 equals to 100 divided by sine 60, which gives us 115.47 Newton. And then to solve T2, we have the known value of T3, so I'm going to put it as T3 divided by T2. Now it's opposite over adjacent, that's tangent, so I'm going to put it as tangent 60, and we know that T3 is 100, so I'm going to change that to 100 over here. So T2 is 100 over tangent 60. Calculating this in my offline calculator, that gives us 57.74 Newton. So that's how you can solve it using the triangle of forces method. Now, if you're required to draw the triangle of forces to scale, just like mentioned earlier, you should be, whoops, I need to reload this. For some reason, it's crashed on me. Copy and paste that again. So when you draw this to scale, just follow the scale that is written in the question, which is 1 cm to 10, which means that, okay, you only have T3 given, right? So T3 is 10, it's 100 Newton. So you need to, you don't have T1 and T2. So all you do is you draw out the vertical line first. 10 Newton is 1 cm, right? So draw 10 cm. Then use your protractor, measure out 30, straight line. Use your protractor, measure out 90, straight line. Then you'll get T1 and T2. Measure the lengths out, use the scale to get the values you need. So if you do this correctly, you will find that T1 has a length of 12 centimeters, which means that it is 120 Newton. And T2 will have a length of about 5.8 centimeters, which gives you 58 Newton. And again, if you want to make sure that's correct, just check against the numbers before. You'll find that, yep, it's close enough. Again, remember, you won't get the exact number because we're drawing it to scale. How are you going to get all these decimals, right? So if these numbers are pretty close, you know you've got it right. So similarly, for the vector force table, let me give you the answer over here. Taking the angle of 0 as the horizontal. So T2 is directly from the center out to the horizontal. T1 is 60 degrees from the horizontal, right? Which means that if you take the Z rule, you measure 60 out here, and that's how you can get T1. And T3 is vertically downwards, and that's how you get the answer for this question's vector force table diagram. Now let's look at situation number 3. So for situation 3, it's given here that we've got three, what do you call it? These are actually three spring balances that have been pulled at different angles at different forces. And we're given the free body diagram over here. So an example of the triangle of forces which you can get would be this. I'm going to draw the 100 Newton force first because it's horizontal. Let me use a thicker pen. 100 Newton force this way. I'm going to label this as 100 Newton. From here, we'll draw F1 going up. So it's up diagonal this way. So this would be F1. And then we complete F2 like this. Let me just make F1 a little bit shorter because it doesn't look quite right. One, and we have F2. Yeah. Okay. So remember, okay, it doesn't have to be to scale as long as our angle labels are correct. So we have F1, F2. Now, if you're not sure how to place the angles, remember that this is always from the horizontal. So let's start with F1. F1 is 40 degrees from the horizontal. So the horizontal is here. That means this is 40 degrees. F2 is 20 degrees from the horizontal. So F2 starts here, right? So what you do is you draw a horizontal line. We're going to make this dotted. This line, this angle, sorry, not line, this angle is 20 degrees. So how this translates inwards, Z rule, this is 20. So now you've got 40, 20. You can remember triangle, internal triangle angle 180. So 180 minus 60, that gives you 120 degrees. So that's how you solve this question. All right, so for the to calculate the unknown value, so we have F1, we have F, 100 Newton. You need to look for F1 and F2. So by using the resolution of forces method, you know what? I kept copying the wrong diagram when I prepared this. Sorry. Let's use the free body diagram instead. That's a lot easier. So you need to resolve the forces of F1, which I will mark in blue, and label here F1x, F1y. And for F2, I'll draw this in green. Let me use this pen. So we've got F2. So this would be F2x, F2y. So to solve F1x, F1y, here's a triangle. So F1x over hypotenuse F1, adjacent over hypotenuse, cos 40. That gives us F1x equals to F1 cos 40. In the same vein, F1y over F1 opposite over hypotenuse gives us sine 40. That means F1y equals to F1 sine 40. And we do the same thing for the F2 triangle, right? F2x over F2 is adjacent over hypotenuse. That's cos, so that's why it's cos 20. So F2x is F2 cos 20. Oops, my writing's getting worse. F2y over F2 is opposite over adjacent. What am I saying? Opposite of hypotenuse, that gives us sine. So sine 20. So F2y equals to F2 sine 20. So this is similar to situation 1 where we have a whole bunch of unknown values, right? Okay, never mind. Let's solve it this way. So you can see here, the verticals are going to cancel each other out. So F1y equals to F2y. So F1y is F1 sine 40 and F2y is F2 sine 20. So we're going to find the values of sine 40 and sine 20 respectively to make this equation easier. So that this gives a 0.643 F1 and 0.342 F2. And if we simplify this further, that means we can express f1 in terms of f2. That means 0.342 divided by 0.643. This gives us 0.532. So I'm going to label this as 1. And next, for the horizontals, we've got two horizontals to the left, f1x and f2x, and one to the right, which means that, you know what, I'm going to do this on the next slide. So I'm just going to do this diagram and put it on the next slide. Here, a bit smaller so there's more space to write. So we can see that f1x plus f2x equals to 100. Now f1x is f1 cos 40. f2x is f2 cos 20. And this sum is equal to 100. So simplifying this, let's find the values of cos 40. This is 6 by the way, in case you're wondering. And also we need to find the values of cos 20. Okay. What we're going to do next is we're going to take number 1 and insert it into number 2. So that's 0.532 f2. So let's solve this. We have 0.766 times 0.532. That gives us 0.408 f2. We're going to add these two values together. That gives us 1.348 f2 equals to 100, which means that f2 is equal to 100 divided by 1.348, and that gives us 74.18 Newton. And then to find f1, because we know that f1 is 0.532 f2, so we're just going to multiply that together. Making this off in my offline calculator. This gives us 39.47 Newton. And that's how you solve this question using resolution of forces. Now, if you want to solve this using the triangle of forces, I keep putting in the wrong diagram, but never mind. Let's get this triangle, because this triangle is going to help us get the answer. Okay, so remember that you can use the sine rule. So sine rule is, remember, it's a over sine a. And I'm just going to write the answer straight away now to make it faster. So it means if we start with, let's say f1. So f1, the opposite angle is 20. So f1 over sine 20. f2, opposite angle is 40. So we're going to put f2 over sine, 40. And 100, opposite angle is 120. So sine 120. So from here, if we want to solve f1, remember you can ignore the in between. So f1 over sine 20 equals to 100 over sine 120. Solving this, I'm just going to write the answer straight away. You know what? I'm just going to write it in full for the benefit of those who need to see it step by step. This gives us 39.49 Newton. And we're going to use the same method, of course, to solve f2. I'm just going to write it over here because I'm running out of space. So f2 over sine 40 equals to 100 over sine 120, which means that f2 equals to 100 over sine 120 times sine 40, and that gives us So quickly keying it into my offline calculator, you will get 74.22 Newton. So if you observe the methods here, yep, you get, again, remember the values won't be exactly the same because we rounded up the values of sine, but they're almost the same, which means that, yeah, you're correct. Then to draw the triangle of forces to scale, we're going to use this as our explanation. I'm just going to get rid of this because we don't need this diagram. The triangle of forces here. Use the scale that's provided in the question, which is 1 cm to 10 Newton. Okay, if you don't know how to get started, what you do is you draw what you know. You know 100 Newton. So 100 Newton based on the scale should be 10 cm, draw 10 cm. Use your protractor, measure out 20 degrees, this is F2, draw, again, protractor again, 40 degrees, draw these two. You will find that they will intersect, and then you measure out F1 and F2 based on what you've drawn. If you did this correctly, you will find that F1 will be about 4 centimeters. That will give you 40 Newton. And F2 will be about 7.4 centimeters, which will be 74 Newton. If you look, close enough. And then for the vector force table, I think you get the hang of it by now, right? So the vector force table will look like this. You get the answer for you. So F is definitely along the horizontal, like this. F1 is 40 degrees from the horizontal, and F2 is 20 degrees from the horizontal. Look at the vector force table, use this protractor to get angles, draw it out, and there you go. So these are the solutions that have been worked out to Tugasan 3 in the module book. So I hope you have found this video helpful and educational. And don't forget to click like. Remember to subscribe to get updates on when more videos just like these would be released, so that you'll find out more on how to solve problems in your physics syllabus. Thanks for watching. Happy studying!